Today we will discuss using neural network for malaria detection. Malaria represents one of the leading causes of global child mortality. In 2023, there were almost 263 million estimated malaria cases worldwide. 95% of global malaria deaths were in sub-Saharan Africa. Here's a chart from the World Health Organization's 2024 World Malaria Report. The colors represent different regions, and red represents sub-Saharan Africa. Early detection of malaria can lead to early treatment, while deep learning to detect malaria could reduce the manual work from specialists and the cost of detecting malaria. Previous studies used images of thick blood smears that were manually annotated for training the deep learning models. In this study, we will be using the same training data but unannotated, as well as a newer version of the YOLO model. Our goal is to find out if we could rely solely on the strengths of the newer model without the manual work required for meticulously annotating the images at a cell level. This could reduce the manual costs required for annotation. In the previous study, the researchers were able to increase the accuracy rate by tripling the sample size by augmenting the images. This is a classic image classification technique that generally has yielded promising results. As such, we used augmentation to increase our training data from 4,832 to 8,165. Augmentation performed include horizontal flip, vertical flip, rotations, and changing the brightness and contrast. You can see an example of an image of uninfected blood smear here. 0 is the original image, and 1 is vertically flipped, and 2 has reduced brightness. And here's an example of an infected blood cell. The technologies used for image classification was YOLO version 11. We used that to train 2 models with different image sizes and sample sizes. We also trained another model using VGG19, another leading image classification algorithm. For data augmentation, we used augmentations. And here are the results. The YOLO version 11 model trained on unannotated images at size 1280 produced impressive results while producing accurate inference with minimal time at about 0.2 seconds per image. Training the model with larger image size at 1280 allowed the model to pick up finer grain details of the images, producing validation accuracy rate reaching 100% in epoch 15 and 99.9% in epochs 12, 14, and 20. Model 4B, which was the YOLO version 11 model, trained on smaller image size at 640, but with more training data, including the augmented images. It did not achieve 100% accuracy, but it produced impressive results and beat the highest performing model previously published, which is Model 3, in terms of precision and sensitivity, and matched the highest performing model in terms of accuracy. The results from VGG19, despite being trained for an extra 10 epochs, which was 30 epochs versus the 20 epochs for Model 4A and 4B, yielded disappointing results with validation accuracy rate at only 74.3%. The implementation of the models include 3 main parts. Firstly, we installed all the packages. We then organized all the image files in appropriate folders. For YOLO, labeling the folders accurately is key to model implementation. We also performed data augmentation for Model 4B. Lastly, we ran the 3 models and reviewed the results, as seen on slide 5 earlier. Let's switch to the notebook to quickly review the implementation. Here we discussed the installation that we just talked about. We installed Ultralytics, which is the company that developed the YOLO algorithm, and augmentation, which we use for augmentation. And these are the packages that were imported. We also set the device to MPS, which allow for faster training on the Mac Studio that this notebook is trained on. For configuration, the first step is to train the YOLO version 11 model. We chose to use image size 1280 times 1280 on the original dataset because the first thing we actually did was to run the model using image size of 2560 and then for 1280 and then again for 640. To see for each of those for only 1 epoch to see how much the training time would be. And as you can see, YOLO allow you to actually just change the image size fairly conveniently, and we looked at the result and found that the total training time by doubling from the image size doubling from 640 to 1280 only required an extra 7 minutes per epoch, but then when we increased the image size from 1280 to 2560, that required an additional 27 minutes per epoch. So we ended up just taking the 1280 times 1280 image size for the first model training. And here you can see that we implemented the training of the model for 20 epochs. And we split the data 80% for training and 20% for validation. And here are the results, and you can see that in total this took about 6 hours and 3 minutes. Over 20 epochs, we saw that the training and validation loss have decreased significantly. These are the results, and these really handy graphs were also produced by YOLO version 11, where you can see that the training loss and the validation loss has decreased to close to 0 over the 20 epochs, and the accuracy has increased to close to 100%. And this is where you can see that the accuracy was really performing quite well for many of them, even after the 7th epoch. It's reaching like 99.7.8%, so the results are very good. It also produces a confusion matrix. As you can see, the x-axis represent the label of the images, the actual label, and then the y-axis represent the predicted label. As you can see that the result for the validation of all 1,206 images were classified accurately, which is very, very impressive. And these are just the percentage of the confusion matrix. And we also looked at the inference time for inferencing one image. And you can also, when you're doing inferencing, you can choose the image size to be whichever size you want to compress it to. So we chose 640 and 1280 to see if there's a big difference. Turns out they're about the same, so there isn't a big improvements. We then went on to train a second model with a smaller image size, but we added augmented data set, and this is the implementation to create augmented data. We imported augmentation, and we created a function to generate the augmented file and save it into, we created a function to generate augmented file from the input folder, which is where the original training images were located, and then we save it to the output folder, and then using the specifically defined augmentation function, and then we add a label to the newly created augmented files. So you can see here that the augmentation function includes horizontal flip, vertical flip, and random rotate 90%. And the augmentation label we used was just to add a underscore to every new files that were created. And here we've created these augmented files to the new folder. We did the same thing for both the uninfected image and some of the infected images, and also, let's see. And here's some example of the infected versus uninfected images that we showed on the slide earlier. And then we trained the model based on these new data. And you can see that the training time is 5 hours, 43 minutes, so slightly less, but not by too much. And the training results, again, they're quite good. Many of the accuracy were like 99% plus. And you can again see like the validation loss and training loss decreased. From the confusion matrix, you can see that we had one false positive where the actual image was uninfected, but it was labeled as an infected image. But the good news is there's no false negative, which means all the infected images were correctly identified, even though they may be mislabeled as the other species. This is good news because it's actually more important to identify false positive and to not have any false negative. False negatives tends to never get picked up by technicians again, so this is actually a slightly better result. And then last but not the least, we implemented the VGG19 model. Using PyTorch, we first transformed the images to meet the VGG19 requirements, created the dataset data loader, and we loaded the VGG19 model. And then last but not the least, we created the loop to start training and validating the data. And as you can see, we've trained the data for 30 epochs, and the training accuracy is very high, but the validation accuracy was not very impressive. And so this actually took the longest time. So in conclusion, I think the key findings, we believe that there are additional opportunities for fine-tuning the models. For instance, we could explore training the VGG19 models with more data and more epochs, or we could try additional image augmentation approaches to see if it helps improve the model's performance. We should also revisit future models, which may be even more effective. Gathering images from a diverse set of geographic locations could also ensure even representations, and it's important to standardize low-cost microscopic equipment to ensure that we're capturing images of blood smears accurately for detection. But most importantly, disease detection is only the first step to a healthy population. The cost of malaria treatment remains prohibitively expensive for an average citizen living in sub-Saharan Africa. We need deep learning discoveries that will result in dramatically lowering malaria treatment costs, in addition to just detection.